You got a finished model, fully trained, and you want to shrink it for deployment. Do you really have to retrain the whole thing just to make it smaller? Copy. No. PTQ, short for post-training quantization, converts an already trained model to lower precision without any retraining at all. It is the fastest, most popular way to compress a model, and you can often do it on your own laptop in a matter of minutes. But there's a catch that shows up at very low precision, and it is worth understanding. Let's dig in. First, let's place PTQ next to its main alternative. Quantization-aware training retrains the model so it learns to tolerate low precision. It recovers more accuracy, especially at aggressive bit widths, but it costs a full training run with data, a pipeline, and real compute. That is powerful, but it is also slow and expensive, and you need access to the training setup. PTQ takes a completely different route. It leaves the trained model as is and simply feeds it a little calibration data to measure value ranges, then converts the numbers to low precision. No gradients, no labels, no training loop, just a quick conversion pass that finishes in minutes. That is the whole appeal, and it is why it is usually the first tool people reach for. So how does PTQ actually work? The recipe is refreshingly short. Watch the 4 steps. Start with the finished, full precision model, exactly as it came out of training. Nothing about the weights changes yet. This is your input, and it can even be a model you simply downloaded, since you never need the original training setup. Then run a small amount of representative calibration data through it. As those examples flow forward, you watch the actual range of the weights and activations at each layer, the highest and lowest values they take. Often just a few hundred sample inputs is enough. From those observed ranges, pick a quantization scale for each layer. The scale is chosen to cover the real span of values without wasting grid points, so the mapping onto integers stays as faithful as possible. Get the scale wrong, and you either clip the extremes or throw away precision in the middle. Finally, convert the weights to 8-bit or 4-bit integers using those scales. No retraining, no gradients, and the whole thing wraps up in minutes, leaving you a much smaller, faster model that is ready to deploy. Strip it down, and 3 ideas capture what PTQ really is. It quantizes a trained model with no retraining at all. You take a finished network and convert its numbers directly, which is exactly why it is the very first thing most people reach for. It needs only a little calibration data, often just a few hundred sample inputs, and no labels. That tiny requirement is what lets you compress a downloaded model on ordinary hardware in minutes. It is quick and easy, but it loses more accuracy at very low bit widths. For 8-bit, it usually stays nearly intact. The trouble is 4-bit and activations, which have wide, outlier-heavy ranges that are much harder to quantize than weights. That is where advanced methods like GPTQ and AWQ earn their keep, using per-channel scaling and error compensation. All right, let's lock in the essentials. Post-training quantization converts an already trained model to lower precision without retraining, the quickest and most popular way to shrink a model for deployment. It works with just a little calibration data to measure value ranges, then maps the numbers onto 8-bit or 4-bit integers. No gradients or labels required. It is the default first thing to try because it is cheap, fast, and needs no access to the training pipeline, so you can quantize a downloaded model on a laptop. Its limit is accuracy at very low precision and with wide activations, which is why methods like GPTQ and AWQ exist, and why quantization-aware training retrains when you need more. Enjoy having AI made this clear? There's a whole library of it waiting for you at standardy.com. See you inside.